Initialization of the population. Initially, the algorithm randomly generates the 0th generation of the population over the entire search space, and the value of the individual zk, q0 in each dimension q is generated according to 8. Where q equals 1, 2, d, rand O1 is a random number, which is uniformly distributed within O1, zk, ql is the lower threshold of the individual population, zk, chu is the upper threshold of the individual population. Mutation. Mutant individual is generated via 9. Where ZP1, ZP2, ZP3 are three different parameter vectors randomly selected from the current population, and ZP1 does not equals 2 does not equals 3 does not equal I, F is an amplifying factor within. Crossover. The crossover process in the algorithm is expressed as 10. Where CR is the crossover probability within O1, and rand O1 is a random number, which is uniformly distributed within O1 and used to guarantee that at least one dimensional component comes from the target vector zk. Selection. Selection operation compares the vector mu kg plus 1 and the vector zkg by an evaluation function, which is given by 11. Therefore, this mechanism allows the populations of the offspring to evolve based on the current population. This optimization mechanism can improve the average optimization ability of the population and converge the optimal solution. Deagle algorithm. In the Deagle algorithm, stegwo.dbn equals impmax reducible for np denotes population size, gmax denotes the maximum number of iterations, ub and pound are the search range. Retest and retrain denote the error in test and learning procedure respectively. Table 2 is the specific procedure employing the DA and the GWO algorithms to optimize parameters CS and gamma S in the RBM SVR deep learning model. The procedure of RBM_SVR_ Deagle algorithm. A hybrid model based on RBM SVR Deagle and XGBoost. This paper assumes that the data set as the input sample is D equals Shidza and the XGBoost model is a linear model, logistic regression, linear regression. The linear model is an additive model. The number of learning trees is n. The XGBoost model uses a pattern of linear superposition to calculate the predicted value, as shown in 12. Here, 11 is a feature vector and I is the number of data points. Hinksy is the regression tree function. H in H is the set space of the regression trees. N, 13, FRMT, Fx indicates that sample x is classified on a leaf node. T represents the number of leaf nodes of the tree. Alpha is the score of the leaf node. Alpha Fx represents the predicted value of the regression tree for the sample. The objective function based on the parameter space is shown in the following, 14. Where omega phi is a regularization term, indicating a penalty value for the complexity of the model. The regular term omega phi in the linear model includes the regular term L1, omega alpha equals lambda alpha 1, and the regular L2, omega alpha equals lambda alpha 2. L phi is an error function that measures the fitting accuracy of the model. I can reduce model bias, such as square loss, exponential loss. Compared to GBDT, XGBoost adds a regular term to the objective function. XGBoost punishes the complexity of each regression tree and avoids overfitting during learning. XGBoost measures the complexity of the tree such as the number of internal nodes, the depth of the tree, the number of leaf nodes T, the leaf node score alpha, etc. XGBoost uses the regular term as shown in 15. In the model parameter optimization process, each iteration model is always added a new function on the optimal model obtained from the previous training. After the kth iteration, the prediction of the model is equal to the prediction function of the first k-1th model prediction function combined with the kth tree, as shown by 16. The objective function can be rewritten to 17. In formula 17, the model's goal is to learn the function of the kth tree. When the error function is replaced by a second-order Taylor expansion, the objective function can be rewritten as 18. When y equals zik minus 1 zik minus 1 a equals 1 and g equals zik minus 12 zik minus 1, the objective function is 19. This objective function solves regression, classification, and sorting problems. Ex. 20, and 21 are in the form of a tree structure of the regression tree function and the regular term. The objective function can be updated to 22. This article defines the sample set on each leaf node as jj equals if equals j. The objective function based on the form of leaf node accumulation is 23. This paper assumes that the structure of the tree is a certain value, i.e., phi is determined. To solve the problem of minimizing the objective function, we can make the derivative of the objective function 0. The optimal predicted score for each leaf node is 24. The formula for the minimum loss function is 25, which can be thought of as a function that scores the tree structure. The tree structure is gradually optimized as the score is reduced. 25 is a function for scoring a tree structure, called structure score. The smaller the score, the better the tree structure is. The algorithm searches for the optimal tree structure by using 25. L** represents the contribution of the leaf node to the overall loss. The goal of the algorithm is to minimize the loss, so the larger part of delta j to eta j plus lambda could be as good as possible. This article expands a leaf node and defines the gain as shown in 26. In 26, delta j to eta l plus lambda is the score of the left subtree, delta r to eta r plus lambda is the score of the right subtree, delta l plus delta rj to eta l plus eta r plus lambda is the score without division, and gamma is the cost of the complexity after introducing the new leaf node. The larger the value of gain, the more loss after splitting is reduced. Therefore, when segmenting a leaf node, we calculate the gain corresponding to all candidate features and select the segment with the largest gain. The core part of the XGBoost algorithm is to obtain the optimal node based on the maximum gain obtained. XGBoost looks for the best branch using a greedy algorithm. The greedy algorithm traverses all possible segmentation points of all features, calculating the gain value and selecting the maximum value to complete the segmentation. The greedy algorithm is an algorithm that controls the local optimum to achieve global optimization. The decision tree algorithm can also be considered as a method of greedy algorithm. XGBoost is an integrated model of the tree. If each leaf is optimal, the overall generated tree structure is optimal. This avoids enumerating all possible tree structures. XGBoost uses the objective function to measure the structure of the tree, and then let the tree grow from depth 0. Each time a branch calculation is implemented, XGBoost calculates the reduction in the objective function. When the reduction is below a certain value, the tree will stop growing. After the boosting tree is created, the XGBoost algorithm extracts the importance score for each attribute. The XGBoost importance score measures the value of features in improving decision tree construction. The more an attribute is used to build a decision tree, the more important it is. In order to further improve the accuracy of prediction and analyze the importance of feature quantity, this paper uses XGBoost to extract the feature quantity importance score. By combining the proposed RBM_SVR_DGO model prediction value, this paper proposes a hybrid prediction model, as shown in Table 3. Hybrid algorithm based on RBM_SVR_DGO and XGBoost.